The last solid principle we are going to look at is open-closed principle, which originated from the work of Bertrand Meyer. You can find more about it in this Wikipedia page. OCP states that software entities should be open for extension but closed for modification. This means that we should write our modules so that they can be extended without their source code being modified. In other words, we want to be able to change what the modules do without changing the source code of the modules. How is this even possible? What is meant by open for extension is that the behavior of your class should be extensible, not via inheritance, which is usually discouraged, but by injection of new behavior into an existing class through abstraction and dependency injection. And thus, we should never go back and change the functionality of an already tested and well-functioning class. I will give you two different examples to show how this principle can be applied in real life. The first example is something that we already have looked at when we covered polymorphism. Assume that we have two shapes, a rectangle shape and a square shape. Each of them has a get area and get perimeter methods that we could invoke to get the area and perimeter of the particular shape. And assume that we are implementing a class shapes that has a method called SumAreas, and we would like to make this as generic as possible. So we want to pass a list of objects that contains different shapes and compute the area of all the shapes that are stored in this list. So one way to implement it is using this for loop where we take the shape, it's an object now. Using the instance of operator, we figure out what kind of an shape this is, then typecast it to the particular shape, and then call the getArea method of the particular shape. So if it is a rectangle, we typecast it to a rectangle and call rectangle.getArea. If it is a square, then we call we typecast it to a square and then call the getArea of method of the square. Let's go over the actual code. This is my rectangle class, this is my square class, and this is my shape class that has a SumAreas method that takes a list of objects and has this for loop and an if-else statement to figure out the type of shape this is, and then typecasting it to the particular shape and calling the getArea. Now at the end, I have a main method where I am creating a list of objects where I'm instantiating one rectangle, one square, and passing it to shapes.SumAreas, and also some perimeters. I didn't talk about it, but there's also some perimeters method that computes the perimeter of the sum of the parameters of all shapes in the system. And this works obviously, but the problem with this is that this code violates the open-closed principle. So if you look at some perimeters and SumAreas methods, they are not closed to modification. Anytime I introduce a new shape to the system, such as a circle or a triangle, I have to come here and add another else if statement with the new shape. So else if shape instance of circle, then do the following, else if shape instance of triangle, then do the following. And the same applies to some perimeters. So bottom line is neither SumAreas nor SumPerimeters methods are closed for modification. Anytime I introduce a new shape, I have to come here and change the source code of SumAreas and SumPerimeters, which is very undesirable. To make this code OCP compliant, we are going to make use of abstraction, inheritance, and polymorphism. Here's how we do it. We first introduce an abstract class shape with two abstract methods, getArea and getPerimeter. Then every shape in the system now extends this shape, abstract shape class, and provides implementation for getArea and getPerimeter. So this is the abstraction and inheritance part of the solution. We then go ahead and change SumAreas and SumPerimeter methods of the shapes class such that both of these methods now take a list of shapes. And we simply have a loop where we simply make a call to shape.getArea. Now I can introduce any shape into the system and I do not have to make any changes into SumAreas and SumPerimeters. They are now extensible, meaning that I can introduce a new shape to the system and they can continue working on those new shapes, and they are closed for modification. I never have to come here and make any changes to the source code of neither SumAreas and SumPerimeter methods, and that's why they are now OCP compliant. Let's go over the actual code. This is my abstract class shape. Now rectangle extends shape and provides implementation for get area and get perimeter. Square extends shape and does the same thing. I also introduce a new shape triangle that also extends shape and provides implementation for get area and get perimeter. I then change the class shapes, the sum areas and sum perimeter methods, such that both of them take a list of shapes, and simply in a for loop they walk over the shapes and call get area or get perimeter. And now both of these methods are open for extension, meaning that any new shape that you introduce into the system, they can continue processing it, and they're closed for modification. So just because you introduce a new shape to the system, you don't have to come here and change the source code at all. Let's illustrate that. In the main method, I am instantiating a list of shapes, then instantiating one object of rectangle, square, triangle, and putting them into the list, then calling some areas and some perimeters methods of the shapes class, passing in the list of shapes, and this should work without any problems. And you could also observe that if I were to introduce a circle object into the system, I can just instantiate an instance of a circle and add it to the shapes, and some areas and some perimeters would continue processing them without requiring any modifications. As a second example of a class that violates the open-close principle and therefore requires constant change, we look at this order management application where we've got items. Each item has a name and a price, and we've got this order class that stores a list of items and then has a purchase method that finalizes the purchase by adding up the price of every item and then computing the tax, and finally printing out the total amount and the amount of tax that needs to be paid. So one way to calculate the tax for an item is to have one private method called calculate tax that takes the price of the item and multiplies it by 0.1 and returns the tax. This assumes that the tax of an item is 10%. But observe that tax computation logic and the purchase method are very tightly coupled to each other. So any changes in the tax computation requires also changes into this method. Let's quickly go over this code. This is my item class with the name and price member variables. This is the order class with the list of items, and calculate tax private member variable to calculate the price of an item. This is my purchase method, and in the purchase method, I'm making a call to calculate tax to get the tax of the item, compute the overall tax, and then print them on the screen. And in my main method, I am instantiating an order object, then adding up the following items: milk, butter, bread, orange juice, and finally finalizing the purchase by calling order.purchase. So let's run this thing and see that it actually works. Here we are. So it just the purchase method just lists all the items, their prices, the amount of total tax, and the total amount that we have to pay. Although this code works, it's not a good design, because anytime there is a change in the tax computation logic, we have to come to this order class and make modifications. So the class is not close to modification. Assume that the requirements change as follows. If the purchase is made over the weekend, then we need to tax the items an additional 1%. So how can we integrate this change into the system? One way would be to pass the day number to the purchase method and also to the calculate tax method, and add that one additional 1% if the day is Saturday or a Sunday. And here is how we can do it. We can now define an enumeration that lists all the days of the week. And now there is an additional parameter to the purchase method that says on what day we are making this purchase, and there's an additional parameter to the calculate tax method that takes the day, and if the day is a Saturday or a Sunday, then it adds this additional 1% to the total tax and then returns it. Go over this code. We have got the enumeration that lists all the days. Now the purchase method takes the day of the week at which this purchase is completed, and also calculate tax method takes the day, and then depending on whether the day is a Saturday or Sunday, adds an additional 1% to the tax. And if we look at the main method, we are making the purchase first on Tuesday and then on Saturday, and we're going to see how the system changes, the amount of money that we have to pay changes. So this is when the purchase is made on Tuesday. The total amount of tax is 120, and the total amount of money that we have to pay is 13.19. But if you make the purchase on Saturday, that there is an additional 1% tax. So now the tax goes up to 132, and the total amount of money that we have to pay is 13.31. So as you can see, the system works. There is nothing wrong with this implementation as far as correctness is concerned. But this order clause still violates the open-closed principle. As you can see, anytime there is a change in the tax computation, we have to come here and make modifications. So this clause is not closed to modification. And according to open-closed principle, once we implement the order clause, we should never change it. It should continue implementing the new tax computation strategies, but we should never come back and change the source code. So how can we do that? The correct way to solve this problem so that order clause satisfies the open-closed principle would be to employ abstraction and dependency injection. Recall our object-oriented strategy, encapsulate what varies. The thing that varies in the order clause is the logic to calculate the tax. So what we'll do is to extract that behavior into a separate interface called tax strategy and have concrete tax computation strategies, standard tax strategy and weekend tax strategy, implement the tax strategy interface to provide their own custom tax calculation logic. We then employ dependency injection to inject the tax calculation logic into the order clause. And here's how we do it. This is now our UML diagram. So we've got the order clause that has a list of items, and we'll now have a tax strategy. So the strategy that implements the tax computation. We have a interface, tax strategy interface, that has the calculate tax method. And now any number of concrete classes can implement this tax strategy. And when we finalize the order, when we call the purchase, we are going to make sure that this order uses one of these concrete tax computation strategies. We're going to inject that as a dependency into the order class and have the purchase method use that to compute the necessary tax. So in this case, the order will be implemented only once. And now we can, it's now extensible in the sense that it can execute any tax strategy that's provided to it, and it's close to modification. So we will never change the purchase method now. This pattern has a name. This is called the strategy pattern, and you can read more about it using the following link. And here is the actual code. So this is the interface, tax strategy. It has one method called calculate tax. It takes the price and it returns the tax amount. Now we've got many concrete classes that provide different tax computation strategies. For example, the standard tax strategy is just taking the 10% of the price and returning it. And weekend tax strategy is 11%. Remember, 10% plus 1%. Of course, I could have combined this computation into 0.11 times price, but I just wanted to be more explicit so that you see that over the weekend the tax is 11%, 10% plus 1%. Now, when we create the order, we provide the strategy in here. We're saying that I want this order to use the following tax computation strategy. This is the dependency injection that I'm talking about. And in the purchase method, we're just going to use that tax computation strategy, the class that has been injected into order, and call calculate tax to get the tax. Now, I can again provide any tax strategy in here, and this class would never have to change. Here is the actual code. This is the tax strategy interface with a single method of calculate tax. There are two concrete tax computation strategies. One of them is standard tax strategy that takes the 10% of the price as the tax, and weekend tax strategy that takes 11% of the price as the tax. Now the order class also changes. We are now injecting the tax strategy as a dependency into order. First, during order creation, I'm supplying the order tax strategy. And also there is this set tax strategy method so that I can change it anytime that I want. Now in the purchase, we're just making a call to tax strategy.calculate tax to get the tax. Let's now look at the main method. I am instantiating an order object. And during the creation of the order object, I am also injecting the tax computation strategy to the constructor. Remember, this is called dependency injection. Then I'm adding the items to be purchased and then making a call to purchase. So this purchase method is going to use the standard tax strategy to apply 10% tax. Then I'm changing the tax computation strategy to weekend tax strategy by calling set tax strategy and then calling purchase again. This time, this call to purchase is going to use the new tax computation strategy, which is weekend tax strategy, and apply 11% tax. So let's see that. So this is the 10% tax strategy, which the total tax comes out to be 1.20. And this is now using the weekend tax strategy, which is 11%. So the total tax comes out to be 132. Observe that this version of the order class completely satisfies the open-closed principle because it's open for extension, meaning that you can feed in any tax strategy, and order class now uses that strategy to compute the tax. And it is closed for modification, so we don't have to make any changes to this purchase method at all, just because we changed the tax computation strategy. We have now finished covering all 5 of the solid design principles. Here are some further references. This is a talk by Sandy Metz on the solid design principles, another talk by Klaus Ilberger on this solid principles, and then there are some links to some further reading